US Physics Olympiad, year 2016. F equal MA, first round. Problem number 23. A uniform thin circular rubber band of mass big M and the spring constant K has an original radius R. Now it is tossed into the air. Assume it remains circular when stabilized in air and rotates at angular speed omega about its center uniformly. Which of the following gives the new radius of the rubber band? Solution for problem. First, let's draw the picture. Suppose that this rubber band is already rotating in air and it has a tension T. And let's check the small segment with a small angle theta. Here we can write equation for rotation of this segment around the center of this rubber band. We have two tensions and they create net force, which is creating centripetal force for this segment. And we have this equation that m omega square r, where r is new radius, and this is centripetal force for small mass m. That's equal to tensions multiplied by sine theta over 2. And now let's check what is small m and what is sine theta over 2. Small mass equal theta over 2 pi multiplied by total mass of this rubber band. And sine theta over 2 for small theta approximately equal theta over 2. We can insert these expressions to our equation and have this equation. So now we can cancel theta and finally find what is tension. Tension equal 1 over 2 pi big mass omega square r. If we have a tension T in this band, we can find what is this tension from extension of this rubber band. So tension proportional to extension, which is 2 pi multiplied by small r minus initial r. And now we can put this in this equation and find what is final r. We have this equation for small r, and the solution is this one. And this is the answer D. So that's the solution for problem number 23. Problem number 24. The moment of inertia of a uniform equilateral triangle with mass m and side length a about an axis through one of its sides and parallel to that side is 1 over 8 ma square. What is the moment of inertia of a uniform regular hexagon of mass m and side length a about an axis through two opposite vertices? Solution for problem. First, let's draw two pictures. One picture is for triangle, this one, and the other picture for hexagon, this one. So for triangle, we have axis of rotation O, and center of mass of this triangle stay on distance 1/3 height from base, this one, and we can count it. And to count what is total moment of inertia for this hexagon, we can see that this hexagon we can split for 6 triangles, 4 of them the same as initial one, and also we have 2 others oriented differently. So we have to find what is moment of inertia of such triangle around axis O. Or we can find what is moment of inertia of this triangle around axis O prime. Let's do this. First, we have to find what is moment of inertia for this triangle around the center of mass. This we can find from parallel axis theorem. So we have moment of inertia equal moment of inertia around center of mass plus mr square, where r is this distance from center of mass to axis of rotation, and the r equal 1/3 multiplied by square root from 3 over 2a, or a over 2 square roots over 3. And now we can find what is I0 for such triangle. And we have I0 for this triangle equal 1 over 24 ma square. Now we can find what is I around O prime axis for the same triangle. That will be axis O prime equal I0 plus m multiplied by 2r square. 2r, that's the distance from center of mass to this axis of rotation. And that's equal to 3 over 8 ma square. And now we can count what is total moment of inertia for this hexagon. That will be this expression 4 times I for 4 triangles plus 2I prime for 2 other triangles, which is equal 1/2 plus 3 over 4 m prime a square. M prime, that's mass of our triangle in hexagonal, because it's 6 times less than mass m. And finally we have 5 over 24 ma square, which is answer B. And this is correct answer. That was solution for problem number 24. Problem number 25. 3 students make measurements of the length of a 1.5 meter rod. Each student reports an uncertainty estimate representing an independent random error applicable to the measurement. Alice. A single measurement using a 2 meter long tape measure to within plus minus 2 millimeters. Bob. 2 measurements using a wooden meter stick, each to within plus minus 2 millimeters, which he adds together. Christina. 2 measurements using a machinist's meter ruler, each to within plus minus 1 millimeter, which she adds together. The student's teacher prefers measurements that are likely to have less error, which is the correct order of preference. Solution for problem 25. Alice using 1 measurement with the uncertainty plus minus 2 millimeters. That will be total error 2 millimeters. Bob measure using 2 independent measures which he added together, so it means that we have to use the root square mean rule. So the result will be a square root from a sum of 2 squares of measurements, which is 2 square root from 2 millimeters. And Christina has the same rule, but with uncertainty 1 millimeters. So that will be a result square root from 2 millimeters. So it means that Christina is preferable. Next one is Alice, and the last one is Bob. That's the answer A. That was solution for problem number 25.